We've talked a lot about even and odd numbers in this class so far, and those are properties of integers. We want to add the recent formality we're learning about now to our experience with working with even and odd numbers. So we say that an integer is even if and only if it is divisible by 2, and it's odd if and only if it's not divisible by 2. Notice that with dividing by 2, there's two possibilities. Either the remainder is 0 or the remainder is 1. In other words, if I take a number b and divide it by 2, I'm either going to have b is equal to 2q or b is equal to 2q plus 1. Those are the two possibilities, and we call the first one even and the second one odd. We're just reformulating something that we have worked with a lot. With that in mind, try to fill in the blanks in these statements. Okay? Hopefully you gave that a try. Building on that, we now consider divisibility by 3 and what the possibilities are when we divide by 3. You have a sentence to complete. If n is not divisible by 3, then n is equal to what? What form does n have? What other form could n have? What are the possibilities for some integer that you'll give a name to, a letter name? And think about how these statements that you're going to fill in here connect with the div and mod operations. What are the possible values of n mod 3? That will help you figure out the two different ways they're suggesting that you can complete those blanks. So we said earlier that 0 is divisible by any non-zero integer. Well, we kind of said it. We explored what you do with 0 and divisibility. Let's make it a little more specific. For any integer a that's non-zero, it's true that a divides 0 because we can always write the equation 0 equals a times 0. In other words, we're thinking of 0 as the b and a is the a and 0 is the q. For example, 0 is divisible by 2, and based on the definition we referenced over here, that tells us that 0 is considered an even integer. In general, if you have any integer b, we know that positive 1, negative 1, positive b, and negative b all divide b for any non-zero integer b. I can always write b is equal to 1 times b, or b equals negative 1 times negative b. I can write b is equal to b times 1. b is equal to negative b times negative 1. Again, I'm thinking of this number here, the second number, as the q in the division algorithm, and this first number as the a. Okay, that tells us that 1 divides b, negative 1 divides b, b divides b, negative b divides b. Those are called trivial divisors of, oops, I just noticed a typo in the textbook. We should say b here, not a. So these are called the trivial divisors of b because they're kind of straightforward. We know that 1 divides any number. We know we can mix plus or minus the right way to get a number as needed. So a divisor of b that's not trivial, we call it non-trivial, a non-trivial divisor. Okay. So 15 has these 8 divisors. The trivial divisors are plus or minus 1 and plus or minus 15, which means the non-trivial ones are all the others. We say a positive integer, a, is a proper divisor of b if a divides b and a is less than the absolute value of b. So we might say a divides b properly. In other words, trivial divisor and proper divisor are related. But notice that proper divisor could include 1 or minus 1. But actually, we said that it has to be a positive integer, so it looks like it would include 1 and anything else. So in other words, the proper divisors of 15 would be 1, 3, and 5. If we're following this definition, it has to be a positive integer such that a divides b and a is less than the absolute value of b. There's a quick remark about different conventions in different books, different conventions among different number theorists. You could include negatives in the definition of proper divisors. Sometimes they don't include 1 or negative 1 as proper divisors. This is why it's important for you to understand how to work with definitions and to verify what definition am I supposed to be using in the given context. So that's a very important skill to have. Example 5.3.5 goes into that phrase that I say I don't like, which is, it is clear. But remember, they're only starting this sentence this way so that they don't start a sentence with a number. It's a style thing. So it says, it is clear that 12 divides 132 properly. In other words, 12 is a proper divisor of 132, which, because 12 isn't 1, tells us 12 is a non-trivial divisor of b. And 2 divides negative 14 properly as well. The integer 11 has no proper divisor. Think about what property 11 has and why it doesn't have a proper divisor. Assuming you exclude 1, of course. So think about that for a moment and we'll continue pushing on that idea. So now take a moment and try this hands-on exercise. What are the proper divisors of the number 132? So you have one of them given to you in this example. Try to figure out all the other ones. Okay. So we want to take the ideas we've been talking about so far and continue applying them to ideas we've already worked with. Another definition that is important for us to work with is prime and composite. We've talked about those before, you've worked with them before. Now we're going to formalize the definition a little bit more. We say that an integer p greater than 1, strictly greater than 1, meaning we're not including 1, is a prime if its positive divisors are 1 and p itself. Any integer greater than 1 that is not prime is called composite. Now before we continue, I want to take this idea and the idea of proper divisors. I'm going to give you an exercise in the homework that's not in the textbook where you're going to connect these two ideas. What do I mean by that? Well, here we have the definition of proper divisor and non-trivial divisor and trivial divisor. These are great words that you could use to try to reframe how you define prime numbers. So I want you to think about how these three definitions connect with each other. And I'm going to ask you to redefine prime using whichever of these words up here you think might be applicable. What are examples of prime numbers? Well, the integers 2, 3, 5, 7, 11, 13, 17, 19, and 23 are all prime. In other words, their only positive divisors are 1 and p themselves. We say that a positive integer is composite if it has a divisor that's greater than 1 and strictly less than that number. Using this definition, because we've excluded 1 in both definitions, we say that 1 is neither prime nor composite. That's one of those things that mathematicians debate with each other, and we're just going to follow the convention in this book that 1 is neither prime nor composite. So before continuing, take a moment to identify the next 5 primes after 23.